Authored by a veteran chemistry teacher, Abdul Shakur, these two textbooks provide all the essentials that would not only enable students to master grade 11 chemistry, but to excel at the next higher level in this subject. What make these texts unique are their creativity and profundity with which concepts are explained for clarity and mastery. The following is one of a set of 44 different tutorials created by the author, using materials primarily from the text Chemistry 11 in Focus. I hope you enjoyed this video. If you liked it, please give it a thumbs up and don't forget to subscribe. We will see you in the next video and thank you for watching.
Today's lesson deals with types of chemical reactions, and we'll cover synthesis or combination reactions, decomposition reaction, single displacement reactions, and we'll do ionic and net ionic equations. Of course, it starts on page 91 and it ends on page 95 from the text Chemistry 11 in Focus. Generally, chemical reactions fall into one of four categories, and these are as follows. You have a synthesis reaction, which is called combination reaction. In synthesis reaction, two or more substances combine to form a single more complex compound. In this type of reaction, smaller species combine to form a more complex one. Now we will use letters of the alphabet and these signs here to represent the reactants and products in the reaction. If you have a species A here, some type of chemical, and this is another species here, if you combine these together, you get AB through chemical bonding. You see here you're combining smaller species. It could be elements, it could be molecules, it could be compounds, and you form bigger ones here. In this case, AB. And specifically, we'll now do some real examples here. So you can have an element combining with another element. For example, if you bond carbon with oxygen, you get carbon dioxide. Of course, you know this is used to produce energy in combustion of coal. If hydrogen is ignited in the presence of oxygen, you get water. Sulfur burns in oxygen, we get sulfur dioxide. Magnesium reacting with oxygen, you get magnesium oxide and energy. Iron reacting with oxygen, you get iron oxide. You can see all these are elements here, and when they combine together, you get these compounds here. This reaction is of interest to us, lots of interest, because if you don't protect iron from the outside air, because of the presence of oxygen there, it slowly corrodes and it forms iron oxide. So this thing is wasted here, and it forms something that's very brittle here, breaks apart. So what happens after a time if you have buildings, such as bridges, and other infrastructure that are made of iron? It must be protected by a special type of coating, painting, or in different ways you can protect your iron. Because after a time, the structures lose their strength and they can collapse. And we have seen many examples like that in some countries. A few years ago, we saw that in the United States of America, where vehicles are passing over a bridge, all of a sudden it just broke into and can be fatal too. Another type of synthesis reaction, you have a compound reacting with an element. In this case, you have sulfur dioxide reacting with oxygen. This is a reaction that is used to make sulfur trioxide that is used in the making of sulfuric acid. You can see, you've seen for the first time a double arrow here. That means it doesn't go to completion, but it's a reversible reaction. The nitrogen oxide here reacts there to give you nitrogen dioxide. This is a carcinogenic substance, and therefore it's important that we do not have this guy around, because the moment it is formed, it spontaneously reacts with oxygen from the air to give you this. So that is a compound reacting with element to the bigger compounds there, larger molecules. You also have compounds reacting with compounds. So ammonia gas here can react with hydrogen chloride gas and you get a solid here. This is called ammonium chloride. Calcium oxide reacting with carbon dioxide, calcium carbonate, which is a solid here. And of course, this is how sulfuric acid is being made when you react sulfur trioxide with water and you get sulfuric acid there. Talk about acid rain again. Sometimes in the atmosphere, when sulfur is burned, it gives sulfur dioxide, and it can change to sulfur trioxide too. And then when that reacts with water there, from the that's there, it forms acid rain. So this is one that I captured on my phone here. It's a synthesis reaction in which ammonium chloride is formed. Here is a bottle with hydrochloric acid, and this is another bottle here with aqueous ammonia. What is happening here is this. The hydrochloric acid produces some gaseous hydrogen chloride gas, and of course you're getting ammonia gas coming out there. Now as these gases come out of these Erlenmeyer flasks here, look what happens. They combine in the air to form ammonium chloride. Observe what is happening here. Even though both of these flasks are giving up the gas, ammonia here and HCl here, you hardly see anything being formed over this mouth here, but it's there. I'll give you a little question just now to ask, why is it here and not there? Now, this can also be done in a different way. This is a glass tube here that's open in both ends. This end is soaked with aqueous ammonia. You soak a cotton swab with that and you put it in that end. And you soak a cotton swab with hydrochloric acid and you put there. Obviously what's going to happen now, the ammonia gas is going to go in that direction and the hydrogen chloride gas is going to come that direction. And you can see the ammonium chloride is formed here is somewhere approximately in the middle there. But it's more towards the left side. It's more towards the hydrogen chloride gas side. Something similar to what happened here. See? The combination is taking place more that side. Okay. Look at this equation here and see if we can answer the question. The rate of diffusion is inversely proportional to the density of the gas. So, what does that tell you? If one gas is denser than the next, it will travel less faster than the other one. The molar mass for hydrochloric acid, hydrogen chloride gas, is 36.5 grams per mole, and ammonia is 17 grams per mole. Which one do you think will travel faster? Of course, the lighter gas will have a less density, and because the rate is inversely proportional to density, the lighter gas will move faster. So now who can answer the question why this is here? It's more towards that side because the ammonia gas moves faster. And the two of them reach up somewhere here before that guy reaches the middle. And that's what happens. So now you know what happens here. The ammonia gas, when it comes out here, diffuses faster than this one here. So it's coming here. So when this one comes out here, it just forms here. So that is a nice demonstration of a synthesis reaction. Then you have what is called decomposition reaction. It's the opposite of a synthesis reaction. This is where you're taking a bigger compound here and you're breaking up the smaller ones here. All right? And of course, you can see lots of decomposition reaction taking place in nature. When things die, they've already decomposed. We'll all decompose. Big structures are broken down by bacteria and other kind of decomposers to give you smaller and smaller compound. That's why dead organisms will disappear when the place starts to get warm. Winter time that doesn't happen because the temperature is conducive to that. So here you have water. If you electrolyze water, you'll get hydrogen gas with oxygen, two elements. Here you can see, I want you to see that, the volume of hydrogen produced is twice that of oxygen. Okay, you have 2 moles of this to 1 mole of that. Sodium chloride in its molten state that you heat it until it melts, and you pass electricity through that, It decomposes sodium here and chlorine gas. Nitric oxide, and it is decomposed into gaseous nitrogen and gaseous oxygen. This is what happens in the catalytic converter here that is made up of platinum and palladium. And what it does, it changes this dangerous gas into nitrogen here and oxygen here. We don't want this to escape through the tailpipe. So your catalytic converter space, I think after these gases come out, but before it exits the gases exit the tailpipe. Here you have a compound and give you an element. Again, you can break this up. It's easy to follow here. This one is interesting. It's potassium chlorate. You give potassium chloride and oxygen, and it is catalyzed by heat and manganese dioxide. If there's a necessity for oxygen, let's say you need to burn a building down, or you just need oxygen for burning, you can create a lot of oxygen by this reaction here. Or if something is on fire already and you want it to continue to burn more vigorously, throw some of these here on top of it, and it gets decomposed by the heat, and it releases the oxygen, and the fire will start to rage. Here is hydrogen peroxide. It's decomposed into water and oxygen here using manganese dioxide here. How do we know it's a decomposition reaction? How can we tell? You see oxygen will start to bubble through the solution, and you can check for this oxygen. What's the test for oxygen? Oxygen will rekindle a glowing splint. So in the mouth of the test tube where this reaction is taking place, you get a lighted splint and you blow it out, it has a glow, put it in the mouth of the test tube, and all of a sudden it gets back the flame. We say the glowing splint is rekindled in that case. You can break up a compound to give you smaller pieces here. Ammonium nitrate give you nitrogen oxide and water. And of course, this is the reverse of that synthesis that we did before. All right. These are some questions there for you to do. You can follow these on the solutions manual. The solutions are there for you. Now we move to single displacement reaction. In a single displacement reaction, this is what is happening. Let's say this is an ionic compound, for example. Of course, an ionic compound has a metal and a non-metal. If you get a metal that's more reactive than this one here, it displaces that one there. So you end up with a new compound here. You have BC, now you end up AC, and this guy gets displaced here. An example of that I usually show my student is a reaction between magnesium and copper sulfate solution. Copper 2 sulfate solution is blue, and magnesium is a shiny metal. When that happens, it forms a colorless solution of magnesium sulfate, and solid copper is deposited or is precipitated. So this is a strip of shiny magnesium here. This is the blue nice copper sulfate solution before the reaction, and this is what happens after the reaction. If you leave this overnight and you come back next day, you will see a deposit of copper there, brown copper at the bottom, and this solution gets clear. And why we get in this change here, because this is blue, and a new compound that is formed is called magnesium sulfate, and that's colorless. And this, of course, is brown. So the blue solution is changed to a colorless solution, and metallic magnesium here gets inside the solution, and this copper here gets displaced here. Why this happens? Because magnesium is more reactive than copper. So anytime you have a compound here with a metal and an ion here, and you insert into that solution an element that is more reactive than whatever this one is, it will displace it and take its place. So this was it before, and this is it afterwards. Single displacement reaction. You can also have not only a metal displacing a metal. In this case here, we're having sodium bromide. If we get another non-metal that's more reactive than bromine, say chlorine, for example, chlorine is more reactive than bromine, and you bubble that through a solution of sodium bromide, you'll get a solution of sodium chloride, and bromine molecules get liberated, and they dissolve a little bit inside the solution, making it look brownish liquid. So this is another type of single displacement reaction where the nonmetal from this ionic compound here is displaced by another nonmetal that is more reactive than that one here. So two ways in which you can have single displacement reaction. Now, ionic equation for the reactions. You may be asked to explain using ionic equation how this reaction is taking place. There are certain guidelines that I have made up for you to follow so that you will not encounter too many difficulties doing these ionic equation. So what I'm saying is this. This will set the ionic compounds into their respective cations and anions. Like I have this copper sulfate here, okay? You break that down into its respective cation. So this is one of the ions and that's the other ion here. Do not separate the cations and the anions of any precipitate form since they're insoluble and do not dissociate in water. Let us say in one reaction you got a precipitate of, say, silver chloride. The fact that silver chloride is formed as a precipitate means that it does not dissolve in water. Had it dissolved in water, it would not have formed a precipitate. It will be in the form of ions. So it is impossible, therefore, to separate the chloride from the silver in that form here. So don't do that whenever a precipitate is formed. Leave it as a precipitate. All right, next. Leave all molecules, elements, and precipitates as they are, okay? If one were to do the ionic equation following these guidelines here, you will leave this, so it comes here. Only these two break up into ions here. And of course, whenever you see something says aqueous, right? That means you can break these into respective ions. So you have magnesium ion here, and you get a sulfate ion here, okay? Now, why we are doing this? We want to show you basically what is happening there, or effectively what is causing the change there. When you want to make the ionic equation, inspect the equation now and see which ions are common on both sides. Here we can see we get sulfate here and sulfate there. Only sulfate ions are common. These guys are not involved in the reaction. They're called spectator ions, right? It's like you and your friend walking down the road, and then another guy and his friend walking down the road. Then there's a fight between your friend and one of the people from the other group. And his friend is watching and you're watching. You're not involved in the fight, right? You're called spectators. We take off the spectator ions, and what is left now is your net ionic equation, okay? So remove that. And what is left now really are two guys who are fighting each other. Oh, so really what is happening here was that the magnesium atom was reacting with a copper 2 ion, right, to give you magnesium ion, and this is where copper being displaced here, okay? So what is effectively happening here is this. Magnesium takes the place of copper in that it becomes a magnesium 2 plus ion. And this guy now, which was aqueous, because it now becomes an atom, it can't dissolve in the water anymore, so it falls down to the bottom. Okay? So effectively, this is what is happening, and it's called a net ionic equation. But some people might want to go further. Why is this happening? Is there something else that is happening? And I want to introduce to you something that is called half equations. You'll be doing that in grade 12, but why not learn it one time here and really understand how this is happening here? So what we'll do is this. We'll break this into two half equations. All right. Remember, this is solid magnesium and atomic magnesium, right? Magnesium wants to gain an octet. What do you think it will do? It will lose 2 electrons. Okay? So magnesium ionizes to form magnesium 2 plus, and it gives 2 electrons away. What happens with copper now? You see, copper now Magnesium forces its 2 electron onto copper ions. This was blue. This is what it causes the solution to look blue. And now it becomes a brown copper atom here. In your grade 12 chemistry, you'll be told that this is an oxidation reaction because it loses electron, and this guy is gaining an electron, and because both of them are happening simultaneously, it is called a redox reaction. But just put that in a box by itself. But it's good to know what is happening here, okay? That change up there is happening. This change is happening here because magnesium is forcing 2 of its electrons onto that one, and itself becoming this. Now in this form, magnesium is soluble, but in that form, this guy is insoluble. All right, do another example for you to see. You can have the same thing happening with a metal and an acid. You would take a piece of zinc and you put it in hydrochloric acid. You see effervescence because hydrogen is coming out there. And the solution of zinc chloride is formed. You'll do the same thing again. All right. Make your ionic equation. Again, leave the elements as they are. So we leave that molecule there and we leave this element there. We haven't seen any precipitate yet. And this, of course, breaks down into 2 hydrogen ions and 2 chloride ions. Inspect to see what is the common ion. You see chloride ions are common here on both sides. So you remove that, and this is your net ionic equation there. Who can predict where the electron is being transferred from what species to what species? You want to do that? Stop the video and do it yourself. Okay, but I can't stop it. I can't wait too long. Zinc. Zinc is what is going to lose 2 of its electrons, and then hydrogen will collect those 2 electrons and form this bubble here. Sometimes I give students a little lab to do. Where I give them some hydrochloric acid and I give them a series of metals, some granulated forms of 4 or 5 different metals. And I ask them to carry out an experiment to rank them in terms of reactivity. You see, the rate of evolution of the hydrogen can be used to monitor the rate of reaction between some metals with acid. This is the theory. The more reactive the metallic element is, the quicker it loses its electrons. And the quicker these electrons are released, the H plus ions can accept them to form molecules of hydrogen. The most reactive element will produce hydrogen at a fast rate. That's what they'll do, and they have to come up with their own procedure and stuff like that, and make their analysis and come to the conclusion, and they make a mini reactivity series for themselves, looking at the rate at which hydrogen is being produced there. You can also have a metal, a very reactive metal reacting with water. In this case, potassium. Potassium reacts very, very violently with water. They give you a solution, potassium hydroxide and hydrogen gas. This reaction is so vigorous that when you put the potassium in the water there, you have to use a shield and do the reaction there. The hydrogen that is produced burns spontaneously. You can see a lilac color. Wherever the piece of metal is zipping around in the water, sorry I can't show you that. I'm not privy to those kind of things anymore. You see a flame is formed on top of the metal there until it burns out there. That's because it's so exothermic, it causes spontaneous ignition of the gas here. And of course, it energizes the potassium there. That's why you see a lilac flame, which is what is produced when potassium salts are burnt. This is a little bit difficult. We have not done this yet. You see, look, water, you don't know that for now, right? Water ionizes to a very, very small extent to produce hydrogen and OH ions. The concentration of these are 1 times 10 to the negative 7 moles per liter. It's 1 over not a million, but 10 million. That's so small concentration it is. So we have a tiny amount of these guys there. Break this up into a little bit of hydrogen and OH here. This breaks up to give you potassium, and you get OH, 2 OH there, and don't do anything to that. Don't do anything to this. Okay? So we have it here. Now the common ion here is, the spectator ion is hydroxide here. Take that off. So what we have here? 2 potassium, 2 hydrogen, 2 potassium ion, and you get this. So anybody wants to make a prediction? What gives off the electron? Of course, you've seen it there. Potassium gives off 2 electrons, and these are accepted by this. Potassium is such a reactive element. These electrons are produced so quickly, right? And then this reacts with it here to produce a hydrogen at a fast rate. Only these metals here are capable of reacting water to produce that there. So I hope that was useful to you.